Then if we have a linear homogeneous ordinary differential equation with constant coefficients of order n, then just like for a second order differential equation, we set up the corresponding characteristic equation and try to solve it. And then the roots or the zeros of the characteristic equation, they kind of give us solutions of the ordinary differential equations in the same fashion as for a second order ordinary differential equations. Only now there's going to be some extra cases. So let me go through it. Let me give you a simple example first. Right? So the fourth derivative of the unknown function minus the first derivative of the unknown function is 0. Then the characteristic equation is r to the 4 minus 1. And then there are 4 complex roots. And the general solution is going to be a combination. Now, 1 here gives us e to the t. Minus 1 gives us e to the minus t. And the pair I and minus I, it gives us sine and cosine t. And so this is exactly similar to second order differential equation. But for a higher order differential equation, it is a bit more complicated. So basically the idea is that whenever we have a real root, then in the solution we have e to the power that root times t. And whenever we have complex conjugate roots, then they're going to give us two exponential trigonometric solutions. So we're going to have e to the power real part of the root times cosine or sine of the imaginary part of the root. Okay, but then at the same time we have multiple roots, and whenever we have a multiple root, then the corresponding solutions are going to be multiplied by 1, by t squared, by t cubed, and so on, up to the sufficient order to fill the multiplicity. So here is an example. So here, when we write the characteristic equation, we see that the roots are 0 of multiplicity 4, 1 of multiplicity 3, negative 7 of multiplicity 1, and minus 3 plus minus 4i of multiplicity 2. Right? So then this 0 gives us e to the power 0t, which is just 1. Well, but then since multiplicity is 4, it means that not just 1, but also t squared, and t cubed. So until we get 4 solutions. So then we have root 1 of multiplicity 3. So since it is 1, it means that we are going to have e to the power 1 times t, which is just e to the t. And since we have multiplicity 3, it means that we have e to the t, then t times e to the t, and t squared times e to the t. And that's all because there are 3 of them. Then we have minus 7, and minus 7 is the root of multiplicity 1. So this is simple. And finally, we have minus 3 plus minus 4i, and these are 2 complex conjugate roots of multiplicity 2, right? So these 2 complex conjugate roots, they give us the combination of e to the minus 3t and cosine or sine of 4t, because 4 is the imaginary part and minus 3 is the real part. But since the multiplicity is 2, we should multiply by t also. So then this is what we are going to get, right? So if the multiplicity were, say, I don't know, 6, then we should include t times this, t squared times this, t cubed times this, and so on, right? So up to t to the 5 times this, because in any case, the dimension of the solution space must be the same as the power, as the degree of the characteristic equation, right? So here the order of the differential equation and the degree of the characteristic equation is 12, so we must have 12 linearly independent solutions in the end. All right, now one little remark. It is actually a very nice and challenging question, and if you like a bit of a challenge, so I suggest that you try to solve it. Recall that for second order linear homogeneous ordinary differential equations with constant coefficients, we have this lemma that all solutions approach zero if and only if the both coefficients are positive. But is the same true for higher order differential equations? So that all solutions approach zero when t goes to infinity if and only if all coefficients are strictly positive. And finally, here is